In the previous lectures, we have been discussing about the modal analysis of beams, and what we observe that even for simple configurations of beams or simple beam models, you can have fairly complicated eigenvalue problem which we have to solve in order to accomplish modal analysis. So, one would be interested in knowing if there are approximate methods which can quickly tell us, give an estimate of the eigen frequencies and the modes of vibration of a continuous system, and for example, for beams. Now, in our previous lectures, we have discussed some of these methods which are used for approximately performing the modal analysis, and as we have discussed that these methods can be improved to improve the accuracy of our analysis. So, today we are going to look at some of these approximate methods applied to beams. So, the first example that let me first enumerate the various methods that we have discussed that we will use also in the case of beams. So, for example, we have used the Ritz method. So, these are all So, the Ritz method, we have also looked at now. In the Ritz method, what we need admissible functions. So, we expand the solution in terms of these admissible functions. On the other hand, for the Galerkin, in the Galerkin method, we use comparison functions. So, suppose we have a field variable u that we expand in terms of these spatial functions, which in the case of Ritz method these are admissible functions. On the other hand, in the case of Galerkin method these are comparison functions. And then in the Ritz method we use the variational formulation. So, we substitute or replace our field variable directly in the variational formulation of the problem with this expansion, while in the Galerkin method we work with the equation of motion. So, these have its own advantages and disadvantages. For example, in the Ritz method it is sometimes tricky to consider non-potential or non-conservative forces, while it is much easier in the with Galerkin method. On the other hand, for Galerkin method, this comparison functions, they have to satisfy all the boundary conditions of the problem, which are more difficult to construct, while these admissible functions must satisfy only the geometric boundary conditions. So, this is an advantage of admissible functions, and these can be very easily constructed using polynomials. Or trigonometric functions. Or other such elementary functions. Now, today we are going to look at these application of the Ritz method for certain problems in beams. So, the first problem is that of the vibrations of a cantilever beam. So, let us consider this cantilever beam. Now, the boundary conditions for this beam, we have discussed this before. We have the displacement at this point to be 0 and the slope also is 0 for all time. On the other hand, on this free end of the cantilever beam, we have the bending moment to be 0 and we also have the shear force at this free end to be 0. Now, since we are applying Ritz method, and in the Ritz method we must we use admissible functions which must satisfy the geometric boundary conditions. Now, these are the geometric boundary conditions. So, whatever admissible functions we choose, they must satisfy these conditions. So, let us consider admissible functions So, if I consider a function like this, So, remember that we are going to use this we are going to use an expansion like this. So, we must choose our admissible functions which must satisfy the geometric boundary conditions of the problem. So, if we consider this to be, let us say, linear in x, then at x equal to 0 this is satisfied. So, psi 1 at 0 must be 0, but when we look at this boundary condition which is a slope condition. So, del x of psi 1 at x equal to 0 must also be 0, but if we choose a function like this, then this boundary condition will not be satisfied. So, from these considerations one can easily come to the conclusion that this must be the function, one of the functions that can be used as an admissible function. Then we can use the higher powers of etc. So, let us first begin with only a two term expansion. So, which means so first use we will first use this two term expansion. So, a1 and a2 are the two temporal coordinates. Next we introduce this expansion in the Lagrangian, which reads so, this is the Lagrangian of an Euler-Bernoulli beam. So, let us consider an Euler-Bernoulli beam. The Lagrangian is given like this. Now, we substitute this expansion in here, and what we obtain, if you and if you simplify this further, so you substitute these expressions of psi 1 and psi 2 and perform the space integration, that means integration over x. These are polynomials, they can be integrated out very easily. The final result So, this is the Lagrangian that you have. Now, this is the Lagrangian of a discretized system with coordinates a 1 and a 2. Now, we can write down Hamilton's principle for this. So, this will give us the equations or equations of motion, and you know that this is going to lead to the Euler-Lagrange equations, which these are the equations for the two coordinates a 1 and a 2, and when you derive these two equations, they are of the form so these are, I mean, this is the discretized equation for the cantilever beam. Now, we perform the standard modal analysis for this discretized system, and we can calculate the eigen frequencies, the circular eigen frequencies, and the modes of these eigen vectors, which can be used to determine the modes of vibrations. So, let us first look at the eigen frequencies. So, when you do this calculation, so this is the first circular eigen frequency of the cantilever beam calculated from this discretized equation, and the second one is obtained like this. Now, if you do the exact calculation, so which we have discussed before, so this is the exact, this turns out to be now you can make a comparison. So, while these the fundamental circular eigenfrequency compares very well with the exact, the second circular eigenfrequency, this is on the higher side. So, as we have discussed before, this Ritz method gives us an upper bound on the eigen frequencies. So, when we calculate by this approximate method, we are going to get this omega 2. Now, what this tells us is the actual eigen frequency is less than this value. Similarly, here also you can see the actual eigen frequency is less than this value. So, this is an upper bound property of this eigen frequencies calculated from the Ritz method. Now, let us look at the eigen functions. So, when we substitute here, we are going to calculate omega and A. So, the eigen pairs. So, we are going to get these eigen vectors, and using these eigen vectors we actually construct our eigen functions using the expansion that we have used. So, we do a dot product So, the first eigenvector that we get with corresponding to omega 1, which is a 1. So, if you dot product with the vector of the admissible functions, so you get the first eigenfunction, and this turns out to be so this a1 vector is actually so this was the a1 vector. So, we take the dot product with this psi vector. Similarly, the a2 vector was actually this. So, this is our eigen function, second eigen function. Now, as we discussed that these admissible functions do not satisfy, I mean they are not required to satisfy the natural boundary conditions, which in our case of this cantilever beam, these are the moments and the shear force and the bending moment being 0 at x equal to L. So, let us look at, so what we have is this must be 0, but since, so this was the bending moment condition, this was the shear force condition. Now, let us see how well these eigen functions satisfy these conditions. So, if you calculate, for example, W1 double prime at L, that turns out, and divide this by W1 at L, that turns out to be and similarly so we are trying out with the first eigen function. We take double derivative of that and see how close to 0 this is. Now, as you can see, with increasing length of the beam, this is going to go to 0 quite fast, and similarly for the shear force. Similarly, you can do for W2, the second eigen function. but since we are more confident about our first eigenfunction. So, here I have taken this example of the first eigenfunction. Now, but I mean this may or may not be satisfactory for the purpose. So, what we can try out is we can increase the number of terms in our expansion So, in the second example I have considered with 4 terms in the expansion, and I have taken the admissible functions in this form. So, psi 1 is the square of x over L. So, I have gone up to 4 terms in this expansion, and when I calculate the following the procedure that we just discussed, if you calculate this eigen frequencies. So, this turns out to be and remember the exact was so this one So, now you can see that with 4 term expansion we have come pretty close to the exact solution. And now once again if you calculate the first eigen function, this turns out to be Similarly, you can calculate the second eigenfunction and third and fourth. Now, we are focusing on the first. Again, let me calculate this ratio, which will tell us how far the natural boundary conditions are satisfied at the free end. So, these are at L. So, now you can see with increase in the number of terms in the expansion, even the natural boundary conditions at the free end, which are the bending moment and the shear force, they are also going to 0 quite rapidly. So, so as you increase the number of terms in the expansion, you are going to get accurate solutions of the eigen frequencies, as well as the eigen functions will also get more and more accurate, and they are going to automatically satisfy they will tend to satisfy the natural boundary conditions which you have neglected while doing this expansion. Now, let us look at this these eigen functions which I have plotted here. So this is the first eigen function. The solid line is the exact, and this chain dotted line is with 2 term expansion, and with the 4 term expansion you have this dashed line. So you can see that the eigen functions, they also tend to go close to the exact eigen functions, which we have discussed in one of our previous lectures. Now, let us go over to a second example. This example is of a plane frame. So, let us look at this plane frame. So, we have this plane frame constructed out of 2 beams which are welded at this point. So, for simplicity we consider that the lengths of both these beams is the same. So, we have L and L. Now, here we have a built in end of this frame, and here it is a pinned end. Now, so for these are essentially 2 beams which have a junction. So, we can treat them like that. So, let us consider that the coordinate here is x, and the displacement in this direction for this beam, horizontal beam, is represented by W1, and this coordinate is y, and the field variable for this vertical beam is W2. Now, we intend to determine the eigen frequencies and modes of vibration of this frame. Let us first write down the boundary conditions. So, at this built in end, so these are the boundary conditions at the built in end. At the pinned support, we have displacement as 0 and the bending moment. So, the coordinate is y. So, this is 0. Now, along with these boundary conditions, we also have this junction. So, what are the conditions at this junction? So, the first condition, say if we consider this beam, the horizontal beam, then there cannot be any vertical displacement of this beam at this point, assuming that there is no axial or this beam is actually rigid. So, there is no axial displacement at this point. In that case, this point of the horizontal beam cannot have any displacement. Similarly, by similar reasoning, for this vertical beam cannot have any displacement in the horizontal direction. Now, since this point is welded, so these two beams are welded at 90 degree. So, under deflection as well, this angle has to be maintained, which means so this is the slope condition. These two slopes they must maintain a certain relation. The second condition is on the bending moment. So, this is of course y. So, there must be an equilibrium. So, from those considerations we can obtain this bending moment condition at this junction. So, now we have all the conditions required for this plane frame. Now, let us identify the geometric boundary conditions. So, here so these are the geometric boundary conditions for the problem. So, we must satisfy. So, when we are following the Ritz method, we have to satisfy these geometric boundary conditions, and the others, the natural boundary conditions, are not so much essential. So, let us now consider this expansion. I will write out this expansion which has been constructed using polynomials. Etc. So, there can be various ways of constructing this expansion. These individual polynomials which satisfy the geometric boundary conditions. So, these are etc. So, I have considered these expansions, but they can be these admissible functions, but these functions can be constructed in various other ways. Now, using these expansion, these two expansions of the field variables, we write out the Lagrangian So, we have written out the Lagrangian for these individual beams, and when we substitute these expansions in this Lagrangian and integrate out the space part. So, here we integrate over x, here we integrate over y, and we obtain the discretized Lagrangian, from where finally, as we saw in the previous example, we are going to get the discretized equation in this form. Now, these are the matrices, the mass matrix and the stiffness matrices, stiffness matrix, and we again perform the modal analysis for this discretized system, and if you do that, then the result for the first two modes So, these are the first two circular eigenfrequencies of the system, which has been calculated using this Lagrangian and the expansion that I discussed just now. So, this figure shows the first two modes of vibration of this plane frame. So, you can see that so this is the fundamental frequency and the corresponding mode of vibration. So, you can see that this angle of 90 degrees being maintained in both these cases, since we have chosen our admissible functions which satisfy these geometric boundary conditions already. So, so this was an example of a plane frame. Next we look at this Timoshenko beam, which is a little more sophisticated model for beam, which considers also the shear deformation of the beam. So, we will consider a simply supported Timoshenko beam. Now, if you recall, the Lagrangian of this Timoshenko beam is given by this expression. Now, in order to simplify this, we use the definition of the shear modulus, and we also define what is known as the slenderness ratio . In that case, the Lagrangian gets simplified . So, with these definition, and we can take out the material constants out and simplify. So, this actually is L tilde. Now, we can let us look at the boundary conditions of a simply supported Timoshenko beam. So, the boundary conditions are obtained through variations. You can write them as so, these are the geometric which we need to satisfy when we are performing the Ritz analysis. So, in order to satisfy these boundary conditions, we can choose we can expand these field variables. for example, psi can be expanded as etc. And W can be similarly expanded etc. So, you can see that these boundary conditions actually can be satisfied. So, psi for example, can be satisfied by using an expansion like this, whereas so if the length is L, then one can use the expansion like this. So, using these admissible functions, we have expanded the field variables, and finally, after applying the variations etc., we will obtain the discretized equations of motion. Now, if you perform the modal analysis of these discretized equations, then the first non-dimensionalized circular eigenfrequency is obtained as 0.612, second one is obtained as 2.087, and so on. The fifth is obtained as 9.889, the sixth is obtained as. Now, there is a reason why I am writing 1, 2 and then 5, 6. There are of course other circular eigenfrequencies in this range, but let us look at the eigenfunctions which are shown here. So, this is the first eigenfunction, and you can see the first circular eigenfrequency. So, and you can see the mode of vibration in the first mode for the Timoshenko beam, and similarly this is the second circular eigenfrequency and the second mode of vibration. So, these two look very similar to a normal beam. Now, let us look at this fifth and the sixth. Now, here there is hardly any transverse displacement, it is very small, not visible in this figure. These are actually the shear modes of the Timoshenko beam, and these frequencies are substantially higher. So, what we have looked at in this lecture today, we have discussed about the approximate methods for modal analysis or for discretization, so to say. We can discretize the equation of motion of the beam, and we have used the Ritz method for discretization. One can also use the Galerkin method in a similar manner. The only thing is, in the Galerkin method, since we use comparison functions, so they are little more cumbersome for calculations to construct. On the other hand, the Ritz method, we have seen the admissible functions are very easy to compute, and if you increase the number of terms in your expansion, then you can also satisfy the or you can also make this this natural boundary conditions which are neglected while constructing the admissible functions. So, you can make these natural boundary conditions also to be 0. So, the satisfaction of the natural boundary conditions. So, you with increasing number of terms, you can satisfy these natural boundary conditions better. So, with that we conclude this lecture.